Commercial aviation has, for the better part of a century, relied on a very simple, if rather explosive, principle. You fill a metal tube with people, luggage, and a frankly alarming amount of refined kerosene. Then, you set that kerosene on fire in a very controlled way to push the tube through the sky. It works remarkably well, connecting our world in ways previously unimaginable. But it comes with a constant thirst for fuel, a significant carbon footprint, and the logistical headache of refueling after every few hours of flight. It's a proven system, but one fundamentally tied to the limitations of chemical energy, a sort of high-stakes, long-distance fossil fuel bonfire. Now, imagine a different kind of tube. This one doesn't need to land for fuel for months or even years. It soars silently through the stratosphere, its engines powered not by combustion, but by the fundamental forces holding atoms together. This is the promise of nuclear-powered flight, an idea that has fascinated and, well, terrified engineers since the dawn of the atomic age. The concept is simple enough to sketch on a napkin. Replace the fuel tanks and jet engines with a compact nuclear reactor and a system to convert its immense heat into thrust. The reality, of course, is a bit more complicated than a simple engine swap. It's less about engineering and more about wrestling with physics, economics, and human nature itself. The allure is undeniable. A single aircraft could circle the globe dozens of times without refueling, offering unprecedented range and endurance. For military applications, it represents the ultimate surveillance or bomber platform, a sentinel that never needs to come home. For commercial cargo, it could mean non-stop global logistics, a world where supply chains are measured in hours, not days. But every gram of that potential is weighed against a mountain of challenges. We're not just talking about bolting a reactor to a pair of wings, we're talking about creating a flying power plant, complete with all the safety, security, and waste management issues that come with it, only now it's moving at 600 miles per hour. 6 miles above your house. This essay will explore the practical realities of that scenario. We will move beyond the gee-whiz futurism and delve into the cold, hard engineering, economic, and societal consequences. What would it actually take to build and operate a fleet of these atomic airliners? What would our airports look like? And, perhaps most importantly, what happens when something inevitably goes wrong? We will not be exploring science fiction, but rather the very real, and often very messy, intersection of human ambition and the unforgiving laws of physics. The journey from a hydrocarbon-powered world to a nuclear-powered sky is not a straight line, and it is paved with more than just good intentions. To understand the sheer scale of this what if, we first need to appreciate the elegant simplicity of a modern jet. Every component is ruthlessly optimized for weight and efficiency. The fuel, a hydrocarbon-based liquid, is energy-dense, and as you burn it, the plane gets lighter. This makes the aircraft more efficient as the flight goes on. The entire system, from the fuel pumps to the turbine blades, is a mature technology refined over decades. We know exactly how it works, how it fails, and how to fix it, which is a comforting thought when you're flying over an ocean. A nuclear aircraft throws this entire, carefully balanced equation out the window. The fuel in a nuclear reactor is fantastically dense, containing millions of times more energy per kilogram than jet fuel. This is its greatest strength and its most profound weakness. A nuclear plane would barely lose any weight during its flight, meaning it would have to be built to handle its maximum takeoff weight for every single landing. The reactor itself, along with the turbines, heat exchangers, and radiation shielding, represents an immense fixed weight penalty. This isn't just an engine, it's a self-contained, heavily armored power station that needs to fly. The airframe must be orders of magnitude stronger and more durable to support the concentrated mass of the reactor for thousands of flight hours. The shielding, necessary to protect the crew, passengers, and ground personnel from a constant bath of deadly radiation, adds even more weight. This isn't a thin lead blanket. We are talking about layers of dense materials, all integrated into the fuselage. The sheer mass of the power plant dictates the design of the entire aircraft around it. This is a systems problem. The introduction of nuclear flight would ripple through every aspect of our global infrastructure. It touches on international law, geopolitics, public perception, environmental policy, and urban planning. It forces us to ask uncomfortable questions about risk and reward on a planetary scale. This thought experiment is not merely about a new type of engine. It's about redesigning our world to accommodate it, and deciding if the incredible power it offers is worth the equally incredible price of its complexity and potential peril. On the surface, the environmental case for nuclear aviation seems compelling, almost utopian. The primary sales pitch would be the complete elimination of direct carbon emissions during flight. A fleet of nuclear aircraft would not release a single molecule of CO2, sulfur oxides, or nitrous oxides into the atmosphere. However, this pristine image begins to tarnish the moment you look beyond the tailpipe. The environmental impact of any technology is measured across its entire life cycle, from cradle to grave. The nuclear fuel cycle begins with uranium mining, a process that is far from clean. The subsequent enrichment process is also incredibly energy-intensive, currently relying on power grids that are themselves often powered by fossil fuels, creating a hidden carbon footprint. The most significant environmental challenge, however, is the one that lasts for millennia: radioactive waste. This high-level waste must be safely isolated from the biosphere for hundreds of thousands of years. And then there is the unique environmental risk of an in-flight accident. The impact could breach the reactor containment, scattering highly radioactive materials over hundreds of square miles. If the environmental hurdles are high, the economic barriers are a veritable mountain range. The upfront capital cost to design, test, and certify a new type of aircraft is already astronomical. For a nuclear aircraft, this cost would be an order of magnitude higher. The price for a single plane would likely not be in the low billions. On one hand, fuel cost, the single largest variable expense for today's airlines, would virtually disappear. This would make ticket prices immune to volatile oil markets. However, these fuel savings would be immediately consumed by staggering new expenses. The cost of specialized ground infrastructure would be immense. The personnel costs would also skyrocket. Pilots, technicians, and ground crews would require years of specialized training in nuclear engineering and radiological safety. Instead, nuclear flight would likely find its niche in two areas: ultra-long endurance military missions and high-value, time-sensitive global cargo. The introduction of nuclear aircraft would necessitate a complete, radical redesign of our global airport infrastructure. The central terminal with radiating gates would become obsolete. They travel via shielded, high-speed underground trains, emerging into a sterile boarding tunnel that connects to the aircraft's forward cabin. The process minimizes human proximity to the reactor section. The single greatest non-technical barrier to nuclear aviation is the profound and deeply ingrained human fear of all things nuclear. Public acceptance would be the final and perhaps highest hurdle. It's one thing to accept a nuclear power plant located dozens of miles away. It's another thing entirely to accept a flying reactor passing 6 miles over your home. The creation of a global atomic aviation authority would be a political minefield, requiring treaties and agreements between dozens of nations, many of whom have non-proliferation concerns. The technology would not be democratized. Only a handful of the world's most advanced and wealthy nations could develop, build, and operate such a fleet. This creates an immediate and stark technological divide. Nations possessing this capability would gain an unparalleled strategic advantage, able to project power and move goods with an endurance and speed that conventional air fleets simply cannot match. This would lead to a patchwork of international agreements, with some countries banning nuclear overflights entirely, creating complex no-fly zones that would fragment global airspace. Countries whose wealth is derived from the export of oil would see the foundation of their economic power slowly erode as a key consumer. Long-haul aviation transitions away from their product. Looking decades into the future, a wholesale replacement of conventional aviation with nuclear power is highly improbable. Instead, a very specific, permanent niche. The skies bifurcate. Most traffic stays with hydrocarbon aircraft. Above them, a small elite fleet in the stratosphere, unblinking surveillance platforms, mobile communication nodes. The commercial niche, ultra-high-value, time-critical cargo. A service worth an astronomical price, justifying the enormous operational costs. The dream of a sky full of atomic airliners remains a dream. The reality, pragmatic, limited, permanent, but rare. The concept of a nuclear-powered aircraft is the ultimate testament to engineering ambition. However, as we have seen, this promise is shackled by immense, unforgiving realities of physics, economics, and human nature. This is not a simple engine swap. It's a complete reimagining of what an airplane is, and the system-wide impacts are staggering. In the end, the question isn't whether we can build one. With enough time and resources, we probably could. The more important question is whether we should. The catastrophic risk, the permanent environmental legacy, and the astronomical cost suggest humanity might wisely choose not to cross that frontier. The power of the atom is most safely harnessed on or under the ground. What scenario should we explore next? Share your ideas below. You've been watching If-Verse, where imagination meets possibility. See you in our next reality.